postdoc and now at Emory, and I know a lot of familiar faces. A lot of you know Lars. And then Elliot is here, Lily is here, and Bo, who is not here. So they're working for a company called Extract, which is, we're doing the work with Extract on actually trying to combine all these ideas and to make them commercial. And everybody who wants to talk about commercial terms, you can talk to Elliot, he's in the back. So let me just kind of try to explain where we are. Why is it not doing this? Okay. Page down doesn't work? Okay. So I'm going to first, here's kind of the outline of the talk. I'm going to talk about deep neural networks, and most of you who are in the data science know everything about it. Those of you who are not in the data science, maybe this will be kind of an introduction. I'll look at a particular type of neural network and the way that we like to look at them. And then we talk about how it meets ordinary differential equations first. So what's the connection between ordinary differential equations and deep neural networks? And there is a straightforward connection. It's actually not very difficult to see that there is a one-to-one relationship. And a lot of the terminology that is known for people in the ODE world is actually being discovered in the neural network world. And there's a language barrier, but I think that after you pass the language barrier, a lot of the things are very straightforward for people in the scientific computing. And I'll try to convince you that it's actually, if you are doing scientific computing, it's actually a really good place for you to be involved because there's a lot of new things you can do with the old techniques you already know. Okay? So that, of course, will, if you understand this, it will immediately say that you can actually design new architectures for deep neural networks. And then we'll take another step and look at how we extend this to partial differential equations and talk a little bit about optimization and maybe a few examples. Okay. So again, so what are deep neural networks? And it has to be a way to do it page down, page up. Does this work? Yes, okay. So the idea is that it's neural networks, which exist for a very long time, which I'll show in a second the mathematics behind it. And it's just that there are many layers. So what do I mean many layers? Well, in the beginning, people say 5 layers are many, but then people start looking at 7 and 10, and right now people are looking even to 1,000 and maybe even more. So the minute you have many layers, they call deep. That's the point of this. And of course, without being deep, they exist for a very long time. So the 50s, I think, were the first ones. But the reason that, of course, they became popular is that they managed to break a few benchmarks, especially in image classification problems. And this really made a whole big kind of comeback of the whole thing and a whole breakthrough for the whole thing. So image classification, face recognition, segmentation, driverless cars, and more. And this is, I made this kind of the beginning of the talk. I must admit, I don't really revitalize it all the time. So I still have the quotes from 2016, but now there are lots of quotes from 2017. So if you look, I mean, to my surprise, you know, when you look at newspapers like the Globe and Mail, you sometimes find something which is close to research articles in the community about, for example, adversarial networks, which I'll talk about a little bit. You find the gist of it in a place like the Globe and Mail, surprisingly enough. And it always bothered me because I would think to myself, like, nobody would have managed to prove a theorem in fluid dynamics and managed to get it in the Globe and Mail, correct? But this field somehow managed to get itself through these kind of things. So people are very interested in this, and there is a big hype. And that's kind of one of the reasons to look at it and to say, you know, what can we do? And now, the reason that, to be honest, I started getting interested in this, I listened to a podcast about technology, and it basically claimed that this was the major breakthrough was computational. Now, you know, I'm considering myself a computational scientist. I go to SciAm Computational Science, to all the meeting, everything else. And here is a revolution that is called on the computational side, and we, computational scientists, has nothing to do with it. That's embarrassing, right, from a computational scientist point of view. So we should be, you know, leading the revolution if there is a revolution in computations, not dragging behind. And I'll try to convince you that we can. It's just a matter of time, okay? So let's try to see what people are doing with this. So people are using it a lot, but there is a bunch of papers, and a bunch of them was in the MIT review that says that, well, you know, people kind of know that it works, but nobody really understands why. And people can build a lot of crazy stuff that can work sometimes, but nobody really seems to understand what exactly is going on. And this is something that we want to understand. So a few things that I'm going to start. So typically when you look at neural network talks, people talk about this kind of structure. So you have an input layer and maybe, you know, hidden layers and something like this. So to start with, I'm going to tell you that this is going to be from now off. I'm not going to use this kind of thing because we invented math, you know, a long time ago. So if you think about this thing, what is this really telling you, this picture? It's telling you that you have basically vector over here, there is a vector over here, there is this thing connects to this plus this, you know. So this we call a matrix, I think, in other places. I've never been to a matrix dots and lines. And to be honest, it takes me a long time to draw these dots and lines. I mean, it takes much faster to write in, like, it takes k times y. So I would leave it with k times y, and I think it's actually much more beneficial for many other reasons, by the way. So one reason is to joke about this, like, no, this is stupid to write it. But the other thing is that, you know, people who actually understand something about matrices know that this matrix K, if I actually think about the matrix, has properties. It can be positive definite, it can be negative, it can be symmetric, it can be H, it can be M. All these things make a difference, correct? I mean, we know they make a difference. So if they make a difference and we think about it for a second, not as squiggly lines, but as matrices, we may start asking questions that may lead to some answers, as you'll see at least in some way. So the general idea is that you have, again, layers, as we said before, and the layers are basically represented that particular layer, add basically a bias, which is a constant to that particular thing, apply a nonlinear function, which is in many cases hyperbolic times or Rayleigh, so the max function, and get an expression. Okay, and they propagate forward like this, and the question is to what goal, and you'll see in a second to what goal. But you do it many, many times. Do it again, rather than doing it this way. And the one that we want to concentrate is not exactly on that one. This was the old representation of neural network, but a much newer representation of neural network, which is called ResNet. So this is residual networks, which was invented by Microsoft. And the idea was that they said, okay, I mean, I'm going to start with basically the Y itself and then add whatever it is over here. And they made it a little bit more complicated, so they made it like a two-layer neural network. So basically there is a K1 here and a K2 here. That's why they made it. You put one activation function over here, so this is the function over here and one over here. That's the way that Microsoft has done this. And the interesting thing that you'll see is when you go to some of these talks, and there's a bunch of really interesting talks online on these kind of things, they tell you don't try to change the architecture too much. But they say, okay, well, you know, we like to break things, so let's try to break it to the first thing. And let's do something like this. First, let's get the second activation out. And for those, they also set some experiments based on this. And then let's add an H. Now, for those of you who have not in the idea of mathematics, maybe they don't see why I added an H, but in a second it will be clear. Okay? So now I represent the propagation forward, rather than the way that they've done it here, as the propagation of this. The next layer will be that layer, plus some parameter H, which I can choose. So I have now two matrices I have to choose. This K2, KJ2, KJ1. So this is like the propagation. Okay, so that's basically what Microsoft residual network is. And the idea is that you take the data, you propagate, 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 propagate. At the end, you get somewhere. And when you get somewhere, what you do is you classify. So what do you mean classify? You take the last step, you multiply it by another matrix W, which you still don't know what it is, but let's for a second assume I know what it is. And I get something here which we call the class. Okay? And then I compare it to a known class. So if I go down, I look at this, and all I do is I propagate with all these machinery here, and I compare the class. Okay, so the forward is I give you an image, you take the image, you propagate, 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 you get the class. Okay? In the inverse problem, I'm giving you a lot of this classified already images. So I give you images, Y's, that I know what their classes are, and I say, well, find me all this K1, the K2, the biases, and the values. That's what I'm supposed to be doing this. And how I'll be doing this as usual. So as usual, they say by optimizing something, correct? So if I'm doing this, I'm going to have an objective function that basically contains some kind of it's not really a difference because we're talking about probabilities, but if you think about it for a second in least squares, you're looking at the difference between the class that we know and the class that we predict, subject to basically having this. Okay, that's really the problem you're solving. Okay, and now there's a lot of things that you have to kind of ask yourself. So you ask questions about what people call generalization, you know, problem of many solutions, robustness, and I'll try to address some of these problems. But this is really the problem they're solving. And for those of you, by the way, again, we've been solving control problem in time domain. This should look familiar. If not, no, we'll get there. But already the structure should look familiar to many, many people here. Okay. Now, first thing, let's talk about generalization. So what do we mean by generalization? And this is where the big thing is that we don't really know we don't still understand. I don't claim I understand it, but this is where the big and interesting stuff that really comes out of this. So the idea is this. I mean, if you have labeled data, so assuming that I have data, let's call it Y1, and I go ahead and I have a label for it, C. Okay? Now, I'm going to take, and I'm going to find these parameters that work for this particular data set. Now I'm going to take another set of images, Now, you can think about interpolation, correct? So if I give you something, and another thing, and something in between, you'll say, great, I mean, that thing's in between, it can work. And to our surprise, this thing works better than simple interpolation. So you can think about if I showed you two cats, and I give you a third cat, which is kind of in between, looks similar, you identify it as a cat. But sometimes, when you actually look at the results, when you try to do it yourself, and you look at the libraries that it's working with, it's surprising the level of generalization. So, and that's something that I don't claim to understand. On the other hand, sometimes it just completely breaks. And then the question is, why did it break? Now, what people manage to show is that when you go deep, you do better generalization. Again, why, we're not really sure we understand, but when you go deep, the generalization usually becomes better. And that's what people manage to show. And this is really where the great breakthrough, because in principle, even a single layer neural network can interpolate any set of data. But it doesn't generalize well. Basically, if I show it new data, it would not necessarily know that it is what it is. But this thing seems to work well, and I mean, that's really a good question about why and what's doing it here. Okay? So again, there's a lot of people working on this particular thing. There's a bunch of papers. I maybe should update this because this almost every week there is another paper or two on this particular thing. Okay? So our goal was to try to understand this problem of local minima generalization, and then if you understand it a little bit better, we can suggest architecture for this particular thing, and maybe suggest new optimization techniques for these things. Okay, so let's first look at this as an ODE. So clearly, I mean, I put an H there for a reason, and that's because if I take this equation on the left, subtract the yj to the other side, divide by h, and take h to 0, then of course that's immediately, calculus 101, that we go ahead and we get a differential equation that looks like this. Right? So now I can interpret this deep neural network as just a discretization of an ODE. That's basically all I have here. So now when I think about it, what it is, it's basically a path finding problem. I have points in space, and I'll go and show you a movie in a second. I have points in space that I cannot really separate them. And what I'm trying to do is I'm trying to move them until I can separate them. Now let me just show you a movie for this. So usually I have to do it like twice because it runs too quickly. So here is an example. So let me kind of go slowly from the beginning. So what happens? You think about this. This is a very simple data set, correct? The data set includes X, Y, and a label, correct? So if the label is red, it'll give one label. If it's blue, it's another label. So basically, the data is X, the location of the X location, the Y location, and the label. So I'm starting with this kind of structure. And clearly, when you think about the classifier, what do we mean by classify? Classify, we're trying to put a straight line and to say on the left is the blue and on the right is the, is it true? The left is, yes, the left is blue and the right is the red. The political map is blue. So we're doing this and we say, can I put a straight line? And clearly I cannot put a straight line through this whole thing, right? So what is this dynamics is doing? You can think about this as an ODE. The ODE tells me that there is a dynamics here. And what I'm doing is I'm basically running the dynamics forward, correct? So I'm putting my K1 and K2, I'm picking them as I go along, and it moves this whole thing in space until it can basically classify. This is, by the way, not perfect classification, you can see, and you can do better if you run it a few times. But basically, I can put a straight line here, and now I can almost classify this completely. Okay? So this is basically what this neural network is doing for you. It's a path planning problem. We have all done path planning problems. So this is start to look familiar to many problems we have done. You can think about it as, yeah, I mean, there is a certain rules that I'm allowed to apply. This is a path dynamic with a particular rules. So let's kind of go back to the rules if I do this. Actually, I should do probably view. Let's see what do this. No? Still have to do it the old-fashioned way. Shift. Okay. So the dynamics is that, for example, the K1 and the K2 are space independent, correct? So they're data independent. It's not that I can choose for any particular point in space to have its own K. It works on all the points at the same time. So these are the rules of the game. The rules of the game is you have K that works on all the points in the same way, K1 and K2, and the question, you are supposed to move them in space until you can basically classify them. That's what we're really trying to do in this business, okay? Okay, so again, this was the idea of the whole movie, and let's move forward with this. So, I mean, I'm an inverse problem person in my training, and you know, did a lot of forward problem as well, because every time you want to do the inverse, you want to do the forward. Now, when somebody gives you an inverse problem and say solve the forward problem, the first question that you'll ask me, did you give me a reasonable forward problem? You give me a well-posed forward problem. Now, typically, somebody who's coming from geophysics or physics, we know that the forward problem is well-posed because usually we have people that worked on this for many years. People prove its existence and uniqueness for the wave equation, for the heat equation. I mean, Navier-Stokes equation for a long time, still an open question for anybody who wants this, but at least for a short time, we know it's okay. So you go ahead and you say, okay, I know the physics is well-posed because people have done this for me already, right? But here, we invented new math. I mean, here, I have an ODE, great. Invented it yesterday, I'm very happy about it. Now what, right? So is it well-posed? Now, you don't want to solve an inverse problem where the forward problem is not well-posed. That is quite obvious because that means that if I have a very small perturbation in the initial data, I will find myself in a very far away place. I mean, you can always run numbers through the computer, that's great, but at the end of the day, if I don't have stability, then there's a problem, okay? So just again, for those of you who have not know what stability is, I'll show again another really small and stupid movie on this. This is kind of just to get the concept going. So it was very fast, way too fast, very stable. So if I need to think about it, I have two dynamics here. You can think about it this way. So I'm running basically a system this is my initial point, and I'm basically running a system in space. And as I'm running the first dynamics, I mean, this is the points that it, let's say, generate for me, okay? And now I'm basically going to start from a nearby point to the first point. So I'm going to start running, this is the end point. Now I'm going to start running from a point close by, hopefully.
So nothing is changing on our screen?
Oh, interesting. Nothing is changing?
No.
Everything is changing on my screen.
I thought I was just missing the point.
Okay.
Looks really stable.
Very stable.
The static piece is often very interesting.
Okay. I'll explain this in any way. Okay. I'll explain this as a static image. So I have 2 points here that I'm starting a path, right? So one of them is going like this, and the other one like this. Now, if the distance between them is growing, right, that's basically what we call unstable. So if you start from 2 points and the distance is growing significantly, that will be very unstable because you're going to get to different points. Now, you can think about it. What does it mean? It means if I try to classify something, and I start at 1 point, and I add a little bit of noise to that 1 point, then I would get a completely different class of things. Now, again, it may make sense in something if you're very close to the decision boundary, correct? If there is red points and the blue points and you're really at the boundary, that makes sense. But when we were classifying, I didn't really discuss, what exactly we're computing. We're computing probabilities. So if the probability of me being red or blue is 51 or 49%, it makes sense that small decision will make a big difference here. Elections can be made by, moving 1% here or there. But if you're looking at, if you're in the 90th percentile sure that you're blue, and I change a little bit, you should not, you should move to 70%, but not to red, correct? That's a big difference here. And that's what would happen if you have an unstable system. So the idea that you want stability, again, is fundamental. And this is, by the way, again, not new to anybody who have done inverse problem in physical sciences. Let's see if I learned something. What was it? Control, Shift, yes. So it's not new for anybody who've done physical sciences, but it's for some reason it's not very obvious to people who are in this particular field because I don't think they come from the same background of ideas. Yeah, we have an equation, should it be well-posed, and when people work for years just to prove stability and well-posedness of that particular set of equations, right? So, but that's that's the first question you can ask. So. So what does it mean? And here's the explanation mathematically, what we try to explain here. But if you start basically from a small enough place, a small enough perturbation, then you're going to end up with a small enough perturbation in the final time. Okay, that's the basic idea. And you will say, why is it important? So here's a nice example of what people call adversarial results, which is a new field or a big field in this particular thing, where people, this is not our computation, this is by guy in Google called Goodfellow. Yes. He has, by the way, a very nice YouTube talk for those of you who want to see this. Just 80 minutes, but still. You have a panda, which is 57.7% panda. You add something which is 0.007 times this. You look at the image, it doesn't look any different. And it classifies this at 99% to be a monkey. So that is not a very nice thing, and that's classical instability, correct? This is classical, I move small thing over here and I get very far over there. It's a little bit not fair because this particular, it kind of looks like random noise, but it's not really random noise. It's in a particular perturbation which is geared towards trying to cheat the system. But still, I mean, it's very, very small. So you should not be doing very, very poorly on this particular thing. Yes? Sure, of course. Why not?
So regarding the previous slide, so you were looking for convergence of the Y matrix. So convergence is a particular snapshot of your dynamics when you can classify at some threshold?
I'm not looking for convergence. Convergence is when you're trying to run, I mean, by the way, convergence is a word that means a lot of things to different people. So I don't even, yeah, so all I'm trying to say is that I'm trying to, I mean, what I'm trying to do is when I look at this one, I'm trying to just look at the small perturbation in the data does not lead to large perturbation where you end up after the dynamics. So you can think about the dynamics that leads to things, think about it like this. You start here and you go to two different directions, or you start here and you say, okay, I'm going closer to each other. That's really what I mean, okay?
So just to make clear, your classification is a snapshot in dynamics where you can clearly define.
Yeah, I define where the final time is. I'm not going to steady state, which is a good question. Somebody asked me this last week. Why don't you go to steady state? And well, I don't. I mean, there's a question if you want to even, but it's not really trying to go to steady state here. Okay. Now, if you look at this thing, then you will realize that most DNNs are not well posed. I mean, why should they be, correct? I mean, you have a random choice of matrices. Why should they be well posed? So that is really an issue. So the question is, how can you make them well posed? So let's start with trying to think about how to make these things well posed. Well, we can start constraining the weighting matrix, and we can design some new things. We can design new networks that will be well posed, and we'll make sure that the discrete dynamic is well posed. That's because, again, we talk about continuous dynamics, but there is a discrete dynamics, which I'll talk about in a second. Okay, so this is a very old theorem, which, by the way, I already mistaken. I quoted it wrong once, so I'll try to not do it again. So the idea is we have an ODE, y prime is equal f of y, any ODE, we have an ODE here. So the question is, when is it stable? So two things really have to happen here. And I'm not actually quantifying it very well. There is a definition. So this is the reason it's actually a little bit embarrassing, or more embarrassing, is that, as Brian says, I was postdoc with Uri. And Uri's specialty is ODEs, correct? And I quoted the theorem from his book wrong. So this is really bad when you do something like this. So, okay, so what do you have to have? Basically, you have to look at the Jacobian of the things. And what you need to have is you need to have that the real part of the Jacobian is negative. That's obvious, because then if it's, or not, sorry, non-positive, I should say, not negative. And the other thing that, of course, the whole thing does not change too quickly. If the Jacobians change very quickly, then it doesn't necessarily go with this. And what is quickly, it can be defined by something which is called dynamic eigenvalues. I'm not going to get into this over here, but it's kind of the gist of the things. Basically, if things are changing not too quickly, then everything will be okay. Basically, these matrices K1 and K2 do not change that quickly, and if basically this Jacobian is negative, then, or non-positive, everything should be okay. So at least we know what can we actually, what do we aim for. And again, it should be clear that if you actually look at K1 and K2 arbitrary, things that you may not want to happen. And by the way, I tried for a while to play with general Ky and K2, and I couldn't find any magic formula to do this. But then we start doing other things, and we managed to look at different things. So for example, I mean, obviously, if I choose K2 to be the identity, and I choose that K1, for example, just the eigenvalues of K1 are going to be smaller or equal than 0, then the continuous dynamics is going to be well posed. And the way to show this, or to generate something like this, is immediately to think about a few things. For example, you can think about taking, again, the K2 to be identity, and this one you just write it as A minus A transpose. And that's immediately antisymmetric. Antisymmetric has only imaginary eigenvalues, everything is okay. So you see, I mean, much better than squiggly lines, because squiggly lines, I don't know how you write antisymmetric. But this one is clearly antisymmetric, and then there is no problem. The other one is to start thinking about Hamiltonian dynamics, and if you ever seen Hamiltonian dynamics, you know that it's kind of the same ideas happen. So Hamiltonian dynamics will come exactly with the same idea. You introduce a dummy variable Z here, which should be kind of like the momentum if you are thinking about this in many ways, and then you just replicate again this structure, correct? So here we already suggested two new structure for deep neural networks that were not really there, and we can start thinking that we can do something with them, okay? The fact that before we had continuous one, this doesn't mean that the discrete one is going to be okay, correct? So before I just wrote a continuous equation, I wrote an ODE. But now I need to discretize the ODE. And remember that basically what we started by saying that ResNet is basically a forward order discretization. Now, one of the first lectures that you take when you do numerical analysis of PDEs, I think Brian taught me this when I was really in graduate school, was that if you look at forward Euler method for advection, which is completely anti-symmetric in principle when you discretize the first derivative, the forward Euler method is unconditionally unstable, correct? Why? Because this is the law of convergence, correct? So if you do want to use one of these two networks, you cannot use forward Euler for this. You have to use a different network. So we have a continuous network, but from there you have to go to the discrete network. And for example, what we changed, we decided to use the Adam-Bashford method, which is actually does stable on the imaginary axis, correct? So you need to go ahead and you need to change the network. And now here we have a new network, correct? Nobody has done this kind of network before, haven't seen it anywhere. And the network looks like this, okay? So now we just invented a new network, okay? Great for us. For the Hamiltonian one, the natural thing to do is to look at Verlet integration. So this is the standard Verlet integration that you would use in order to do these kind of things. And it's a symplectic, and there's a lot of theory about it. It's not that important right now. The nice thing about these kind of network, by the way, that it's reversible, means that you can actually go forward in time and you can go backward in time. And that's actually important for derivatives. I'm not going to talk about it that much unless somebody wants to talk to me about this more after, but it's actually very important for derivative calculation and saving memory. Okay? But here we have a new architecture, a new dynamics. Okay. Now, what I like about this nice what we just discovered here is that, well, everybody who was taking an ODE course know that there is a zoo of methods, correct? I mean, there is all these multi-step methods, there is implicit methods, there is Rangakata methods, there are all these kind of things. Now, since we're kind of BC, it's late, I can say whatever I want, although it's recorded, it's dangerous. I would say that machine learning people have a specialty to invent new name for everything which is already known already in math, okay? So this is your chance, if you are really want to be famous and rich, is to come up with an old ODE method that people have already done before you, invent a new name for it, and you may be rich and famous. I mean, this is what people have done in this thing, because again, I mean, there are so many of them out there. We just have to grab one or two and you can do it. So it's something that you should try to do. Okay, so let's think about now how do we solve the optimization problem. Optimization problem, I need to compute derivatives. And if you ever integrated something and you do derivatives for ODEs, then you know that this basically comes as a back propagation. So you propagate backward in time to do this. And it's actually really surprising that the adjoint method is just back propagation. I mean, or vice versa. Adjoint method is known a little bit before, I would say, but only a few hundreds of years before. But again, invented as back propagation without actually acknowledging that there is actually the two things. And we can actually now, if you understand these two things, now you can compute, you can use Gauss-Newton, you can use all the machinery that we kind of have already in many other fields to try to solve these kind of issues. Of course, you can start thinking about multi-level optimization. So if I understand that this whole thing has a dynamics that takes me from, let's say, 0 to 1 in 20 time steps, I mean, what is 20 time steps? I mean, can I want to take 40 time steps? Well, it's just a discretization, correct? So there is no problem moving, for example, from more layers to less layers. And that's, by the way, what I like about thinking about continuous analogs. The reason that we like continuous analogs is not necessarily that we actually try to necessarily stick to the continuous analogs. After all, I mean, we're applied. We're not pure mathematicians who really want to have something for order of h to the fourth or something. But the idea is that when I want to move from 20 time steps to 40 time steps, if I look at this and I ask somebody who doesn't think about the process as a continuous process, how do you move? And there is no really clear answer. If I really think about this as a time integration, and I say, okay, so I introduce new points in the middle, correct? And I can interpolate between them. And that's how I move between 20 time steps to 40 time steps. I've done this many times in other fields, and again, this reasonably work well over here. I'll show you an example in a second. Okay. So I want to show you an example for this, and to show you how this works again. So it will be another movie. So I'll start by showing you, what did I do with the, it's a good question, what did I do with the movies here? So hopefully this will play. Okay. So I'll try to go to the beginning. This is the beginning to the end. Does it work? Yes, this time it does work. So I have here 5 different classes, okay? So the green class, the purple class, the whatever class, okay? And they're not convex. I mean, this is not like an easy problem to classify, right? I mean, you can't draw a straight line that separates anything from anything. And you think you'd like to do this. Now, you can use resident, which is the typical one with K1 and K2 to try to separate them. And again, there's no stability guarantee. So it will separate them eventually. And what it would do, and this is what it does when we run it, it basically go ahead and it, this question, does it run? Does it run for you? Yes. It basically spreads these points over a big space. And actually, it's hard a little bit to see, but in principle, if you actually pass like one line here, one line here, kind of there's a combination of lines that you can divide the space. But these points have spread over a large domain. So, and especially if you look at the yellow points, they kind of move from one side to the other side. Clearly, this is not a great way to classify things, correct? Now, if I go and I say, okay, what would happen if we use a stable network for this? If I can even get out of this, yes. So because the dynamics is bounded, it cannot really go too far away. The dynamics is basically doing what it's doing, and eventually it's organizing in its way that is much more reasonable to settle down. So this is, again, the difference between a stable method to an unstable method. Now, the more data you have, the least chance that you're going to get unstable dynamics, because the data basically compensate for everything. So you can think about if the space is dense, everything becomes better. When the space is sparse, things are not becoming as good as they are. Yes?
So in this case, do you actually try to bound the real part of the eigenvalues of the...
Well, it's already bounded because for this one I use a Hamiltonian dynamics. So it's bounded by just the construction of the network, right? So the network is already, I mean, one way you can say, I'm going to compute eigenvalues. The other one you say, why compute eigenvalues? Let's just generate a system that is like this. And I say this many times to people, if you come from physical sciences, so if when Brian decides he wants to work on, on a particular set of equations, correct? You're working on this very set of nonlinear set of equations a few years ago. I forgot which ones. Well, he's stuck. That's it. That's the system of equations he's working with. He committed. Now he has to work on this system of equations. Here, you work with this system. You don't like it, you change it. I mean, it's open. I mean, nobody says it has to be this system or that system. The only thing is, I mean, many different types of dynamics would lead you to similar things. You have to decide which one you want. Okay, let me just speed up a bit because I'm looking at time and people want to come home, I'm sure. So, go back. What did they say? I say that it's going to be like, no, like this. Okay. And so again, I mean, you can look at difference, like when you do unstable classifier, when you shape it back, you'll see you get some kind of lines like this in between, or some things like this when you don't have enough information. But when you do a stable one, things become much nicer. Okay, so let me go back so this is ODEs. Now let me go to PDEs. For that, I need to introduce convolution neural network. It's the same thing we've done before. The only difference is that this K's that before were matrices, like any matrix, dense matrix, whatever you want. Now this is not, it's not a regular matrix, it's a convolution. So basically convolution, this is something I always have to say to people that have not really seen before. Convolution is just a matrix. Okay, it's a linear operation, which means it's just a matrix. With a certain structure, circular matrix, with certain coefficient, with certain sparsity structure, but it's a sparse matrix, that's what it is. And if you think about it, Laplacian is a convolution, correct? I mean, it's just a convolution with a particular entries on the whole thing. So in the convolution, this guy and this guy are just convolution matrices which you can apply, okay? And what I want to convince you first that convolution is really a PDE. I mean, shouldn't be really that new, but if I think about the convolution in one dimension, so let's say I want to convolve this K1, K2, and K3 with a big vector that's in one dimension. Then I can go ahead and say, why K1 and K2 and K3? I can say, let's change bases. So for example, it would be 0, 1, 0 with S1, and S2 over 2H with this particular one, and the S3 with this particular one. Now, why do I change the basis? Because of course, as H goes to 0, this goes to basically the identity, this goes to the first derivative and the second derivative. So when I do convolution neural network, rather than trying to find out K1, K2, and K3, I can think that all I'm trying to find out is the coefficients of the derivatives. Okay? So, and by the way, for those of you who've been involved, for example, with full waveform inversion, I know there's a few people in the crowd here, that's what we do, correct? I mean, you have some kind of a wave equation with unknown coefficients, and you try to find the coefficients. No different. It's the same idea, right? So now you come and you say, okay, I have a convolution model. What can I do to make this thing work and make something that I actually understand and will behave in a way that I want to actually understand? So for example, you start looking at this, and after you blur it enough time, you say, wait a minute, if I put K2 to be minus K1 transpose, I would get a parabolic ODE. So rather, we should really start thinking about this network, not just as neural networks. That's my first claim. We should start thinking about this neural network with names that actually mean something, and mean something to what kind of behavior they would have. So for example, I would call this a parabolic neural network because it will behave in a parabolic way. Basically, as time goes to infinity, things will start to decay, correct? And I will get things that will behave in a way that the heat equation kind of behaves. That's what I expect to see here. In the same way, I can come up with a new design. Sorry, by the way, this is the discretization for these particular things. And just by the way, again, if you look at space scale, and for those people who looked at this thing before, this is exactly what people have done in image processing for scale space. It's not that different. The only difference is that in scale space, people usually assume they know what K1 and K2 are. Here, we just have to learn them from the data. Okay? Now, you can think about a different one. You can say, again, I mean, here's another inspiration from PDEs. You can say, why am I using always the first derivative? First derivative is nice, but I can use second derivative. Who says it has to be only one derivative? So why should we look at U double T, right? And now I get something which looks like this. So I will use a leapfrog method. The leapfrog method will do exactly this. And this is what people call, again, reversible architecture, because if I know what happened at yj minus 1, I can solve backward in time. So by the way, this is, again, implication from memory. And I would call this, again, a hyperbolic network, because it behaves like a wave-like equation, not like a, so if I want to, so here's something which you can get some intuition. We know that parabolic equations decay information, correct? Information is lost. And hyperbolic equation, information is actually conserved. So we basically carry the information forward. So now you can start asking yourself, what tasks do I want my neural network to do? Do I want it to classify something? Maybe I don't really need to keep all the information. Who cares if to identify a cat that I see all its whiskers? But if I want to, for example, predict some way that an image is going to do something, so I want to look at a movie, I want to look at the next frame, or I want to look at something happening, I want to preserve information. So these kind of things, maybe the hyperbolic networks are better. So to start thinking about not just the names, but what does it mean and what can it do for me, because I understand their properties, and again, it's not just random matrices anymore. Okay? So here's an example I wanted to show you. Last two movies, I promise. So here's an example when we run. So this is the clown, and we basically run, well, you tell me, what am I running now here? So this is one network, okay? And then I'll show you the other one, just to kind of as a contrast. So which is which? Which one is parabolic? Which one is hyperbolic? So if I look at information that is conserved, I mean, look at this one and look at the wiggles, hint, versus the other one. Where's the other one? The other one disappeared on me. Let's just close it. So this was, I don't remember, this was the one with all the wiggles, okay? And the other one maybe kept edges, by the way, a little bit, but that's because of, but you see how information is being smeared, correct? Information, basically, look at all these things. The information is being smeared as I go along. By the way, if I plot a color bar, it would be easier to see this. So information is smeared, things behaving in a parabolic way. If information is kind of oscillating, this behaves in a hyperbolic way. That's the... These will be my filters, correct? So usually if you think about it, you're propagating a bunch of different filters. So I'm propagating here 9 different filters, correct? That's what I'm doing. Okay. So, what did you say? Okay. So the other thing we can do with this kind of thing is think about multiscale, to move between different grids, to think about all these kind of things we've been done in the previous work in ODEs and PDEs. We can think about starting with what people call image pyramid, again, because now you understand how to move between different scales, correct? So if I understand how to move between different scales, I understand how to solve the problem on a coarse scale and upscale it slowly. People are doing this in many other fields regularly, correct? So I'm not going to actually go into this, not at this time of the evening. I'm just going to show you some results from this. So for example, if you look at the MNIST example, and you look at convolution, okay? So here is a coarse scale, and here is a fine scale. Right? You take the fine scale, and you have a fine convolution. You take the coarse scale, and you have a coarse convolution. And you look at it, the convolution matrix, this is a three-way flow. You look at the color scale of this, and look at the color scale of this, and it's not the same. Convolution does not look the same. This is different, right? And the reason it's different is because you basically use a coarsening strategy for multigrid to take one operator and coarse into a different grid. And the outcome, of course, does look the same, right? So that's the basic idea. If you look at combination of first derivative and second derivative on one grid, the numbers are not going to be exactly the same as if you just change the h for a different grid. So things are looking different, and you can see the numbers here. But it's not, all I'm saying is that it's not trivial to move from one mesh to another mesh by just saying, oh, I'll stay with the same convolution and just move to another mesh. You have to do a procedure similar to what you do in multigrid. When you're moving from one mesh to another, you're coarsening your operator. Do exactly the same thing over here. Okay? And again, all of us have seen this before. Okay, so here's some work that actually Lily here has run. So this is trying this kind of thing on STL10, and this is very old work. It's already like 4 months old. This field, everything is moving extremely quickly. You never know what published tomorrow or something like this. So we just look at, there's a website that kind of puts everything together, and this is from 2013 to today, and this is done at Extract, so you can see that this is a much better result on this particular data set. This particular data set is actually, in some ways, it's easy, but it's hard. I mean, there's only 500 images per class, and so it's not a lot. It's not like other data sets that exist, like maybe 10,000 or something like this per class, or 5,000. This is a really small data set per class. So in some way, there was a lot of room for improvement. Versus other data sets, for example, that the number of images per class is so big, there is not much room for improvement over here. So you can actually do a much better job here because there is, again, so much room to improve. And the second experiment that I'm going to show you is, again, on MNIST. This is the usual data set, but to be honest, it's a well-known secret. Everything works on MNIST, so if you really want to feel good when you do your first steps on machine learning, use the MNIST data set. You'll get a really good feeling that your method really works. Okay, later on, the harder data sets, no, but this one is. And what we're doing here, we're doing something like this. We're running this on different layers. We're going to start from 2 layers, then we're going to move to 4 layers and 8 layers. We're doing continuation, multi-level continuation. So this is the objective function that we're minimizing, the cross entropy that we're trying to minimize. And this is what the validation accuracy is. Okay, so let's look first at the objective function. So we start with 2 layers, and we're doing it twice. So we're running it with random, starting from random every time, and running it again, just continuation. So in the beginning, there is really no running it twice randomly. Luckily, one of them is a little bit better than the other. Okay, fine, but that's not really important. Then you take the 2 layers and you interpolate the 4 layers. Now again, if I look at a continuous setting, I know how to move from 2 to 4. Basically, I just interpolate. And you can see a slight increase in the objective function, then later a decrease, and actually do better than D, right? And by the way, here, notice that we're not really trying to do a computational game. I mean, in principle, we train them at the same number of iterations. But I mean, you can say, why are you doing here 10 iterations or 20 iterations? You can stop after 3 or 4 or 5. I mean, you can save something. But that's not the point of this particular experiment. It's just to show how you can actually do something here. And you can see how it continues on and on and on. And by the way, every time you're adding layers, you have a smaller, you're paying a little bit less in the accuracy, because, and that's of course implied, because it converges to some kind of a continuous analog. So the 32 layers and the 64 are very close in terms of what they describe. Okay? And every time I start from scratch, I start from scratch. Sometimes I do a little bit better, I do a little bit worse, but overall, I'm really gaining from the fact that I'm actually interpolating over time from the previous one. The same thing happened on the validation, more or less. Again, sometimes I do a little bit better by luck, but most of the time I'm not doing as well as I'm doing by just solving, doing continuation on the whole thing. So that's a second thing that shows you why it's worthwhile doing these kind of things. This is being done on part of ImageNet. So Song, who was, yes?
I'm sorry, I think I lost it somewhere. So you're presenting here your results,
Mm-hmm.
experiments, but any particular network, or is it just?
This was with the Hamiltonian network. Okay, this was the
All those experiments are
maybe the last ones are not. If when I see it, I remember it. Everything that we've done until right now is the older one. So in the beginning, we just did Hamiltonian. Then later on, we started being a little bit more sophisticated. So this was, again, the Hamiltonian network. And this particular one, what we did is, once again, we basically did something like this. We started, there's two options here. Either you do continuation, right? So you do multigrid. Basically, this will do space. So you basically try things from, you know, from coarse image. You classify the coarse image, then you get the results. You take the weights, you basically update them, and you can go wider. And again, people here that doing full waveform inversion are doing it all the time. That's the standard way to do full waveform inversion. You start by low frequencies and then increasingly increase your model. And you can see that if you don't do multigrid, again, you're doing it on different image dimensions here. So you start with low resolution to high resolution to high resolution. And to be honest, the difference in results, I would say, because of random miniaturization. I don't think that there's any reason to believe that this was necessarily really much better than this. Okay? But when you're actually doing it with the multigrid continuation, again, when you're doing this one, you started from the results that here, and that really gives you an improvement, and the same thing happens in the last point here. So you're gaining something from the previous coarse meshes that you'd see here. And by the way, in this particular experiment, we gain quite significantly over this. And again, I don't have any theory or anything that will suggest that this is really true, but in other fields, when you actually do continuation from coarse to fine meshes, you tend to get away from local minima. It's a well-known phenomenon. I'm not claiming it necessarily happens here. You need to do much more work to show anything about it, but this is something that we know in other fields. Okay, this is just the same thing. I'm not going to go over this one. And this is showing you that even with, by the way, this is a very, very naive implementation, showing you that in computational time, we actually gain something going in computational time. Now, by the way, there is a whole new field here which needs to be explored. So when you're starting basically a warm start or hot start in a continuation for multigrid, there is a theory that says that if you do multigrid and Newton method, one iteration would be enough in order to converge as you're refining the mesh. So there is a well-known theorem about mesh independence of Newton method. There is nothing about stochastic gradient descent, nothing. Nothing that I know of, nothing that I heard of. No connection between stochastic gradient descent and anything else. It's an open mathematical problem. How would stochastic gradient descent behave as you're basically starting from a hot start? When you're getting closer, what do you do to the iteration counts? What really happens? I actually don't know. And all we see is we observe some stuff here, but we don't really know what's going to happen. Okay, so I want to conclude because I don't want to be over time, especially not at night. That first thing is I think it's interesting to think about DNNs and CNNs as dynamical systems, ODEs and PDEs. And a lot of people that are in this crowd that know a lot about ODEs and PDEs can actually, I think, really contribute to this particular field. I think that there is a lot of things that we can actually do in order to enhance the state of the art in this field. And it's using tools that we know. Okay? And I think this is really, really interesting. The second thing is I want to actually say that the usual theory works. So when I start looking at this, some people tell me, oh, nothing that you know from computational science will ever work here. And I think they're completely wrong. I think everything we know for computational science actually works here. So, when you have an unstable network, sure, your intuition, what happened is I think a lot of the times if people were getting results that they try something, it doesn't work, then they did some small thing and suddenly it works. It's all symptoms of instabilities. And we know this. We know that if you have an unstable system, you do some small change in your code and suddenly things behave very differently, right? But if things are stable, then I'm sorry, but it's boring, correct? Nothing amazing will happen. It's a sign of, we're boring people. We like boring and predictable stuff. So that's what I would claim, that you have to be a little bit careful. And of course, how to do the shortcuts, that's a different story. Some shortcuts will be important here. I think it's important to understand that we can change the architectures of DNNs. And I think we need to do more about adding constraint to the optimization and to make sure that things actually connect. That right now the optimization that we're using is very naive. It's still stochastic gradient descent. It doesn't really do much in terms of using all the knowledge that we have on the PDE itself. And that's something that needs to be done. Okay, and with that, I think that I'm done.
We will have some time for questions, and then we'll break for the reception, and you can ask questions after that. But yeah.
So did you try to run adversarial examples against?
Yes, and we have some mixed results that needs to be further understand. Now, the adversarial result is a little bit more. I can talk to you much more about it. So there are two parts here. There is the network part, and there is the classifier part. So forget for a second everything about the network. You can just try to see if your classifier is really stable to if the classifier is not foolproof, then you can just cheat the classifier, correct? So now the question is, what is the part that is screwing you up? Is the network or the classifier? And what I find that most of the time is the classifier is going to be the problem, and then there's a question how to fix the classifier, which is a different story.
So the ODE formulation for the deep neural network, that I don't know, like it got me thinking about recurrent neural nets. Do you guys do anything?
So I look at the structure. It's the same structure. So if you think about it, actually, kind of go back quickly. Yeah, it's simpler. So let me just go back to anywhere that we just have an equation. Okay, so let's look at this one. So in recurrent neural network, the only difference is that k would not depend on t. K is constant. That's it. That's the only difference. So yeah, you can use exactly the same thing. Yeah, much simpler. We did some work on recurrent, but we didn't really push right now the thing. But it's, I agree with you, much simpler because the only difference is that k is constant. Nothing different because besides that.
Yeah, and that's usually the ones that are plagued by instability and diminishing gradients.
It's the same phenomenon, exactly the same thing. Nothing fundamentally different here. So, but again, as you said, easier, less parameters in principle, and the only thing is that you just say, okay, k1 is, I mean, the k does not depend on time. The k is now constant. That's it.
My next question is related to, so you showed the accuracy results for the progression in years to extract the accuracy. I wonder, the dimensionality of the network, how does it differ? Do you get that accuracy with more or less?
So I don't remember, maybe Lily remembers. But I'll tell you one thing here which is interesting, just to kind of look at it, look at this one. So just to think about this way, if K1 and K2 are different, you already have double parameters, right? So think about any ResNet, any typical ResNet will have double the parameters we have. I don't think that the number of parameters is really important here. It's really the number of convolution here is really important because that will be the cost.
Yeah.
But it's the number of parameters is smaller actually. It's about half to start with, right? If you do the same thing, because K1 is equal to K2, right? The transfer. So.
Lillian, I think you had a question?
So it seems like this ODE process is just transmapping the data to a way that we can classify.
Yes.
I don't understand, and it seems, if that is correct, the mapping should be related to the classifier that you use at the end, but I don't see it in the derivation.
So the map, I mean, the ODE does not necessarily, I mean, the ODE has nothing to do with the classifier when you write it. When you optimize it, correct? So when I go to the optimization, let's go, I don't know, anywhere. I'm trying to find the optimization problem.
There was a big S.
Yeah, there was a big S somewhere. Trying to find that S. Was it here? Here. So if you're minimizing this S, correct? The S is going to be determining what is, when you're doing the back propagation, is going to propagate the information from the S into the whatever classifier you have. So the K that you're going to learn or to optimize upon will depend on what objective function you're using, correct? And that's where the classifier is coming. Okay?
So the aspects of the dynamical system that you basically use to kind of classify the hyperbolic versus parabolic dynamical systems here, those are very gross descriptions of the different kinds of dynamical systems that one might study.
Sure.
Like there are many other phenomenological things, like what's the maximal in time behavior, how fast does it converge, is there a strange attractor, there's all these other descriptors of ultimate behavior in dynamical systems. What's the impact of all of that structure in dynamical systems here?
I'm actually waiting for people like you to tell me. So, I mean, all I'm doing right now is point to this particular thing, and I think that, again, I was in Cambridge last week, and talking to a lot of people that, you know, are I mean, I'm not really a mathematician, as I told Brian. I mean, I know nothing about math. But there are people that really know math. I mean, they can really start proving theorems. So, for example, I had a long discussion with Martin Burger on exactly the parabolic one, and we actually managed to prove something, right? I mean, I'm not sure how important it is. It's a good question. There is a good question about how important, when you prove something, to the actual application, so attractors. Are they important or not important? It's a good question. I don't know what the answer for this is. For example, for the parabolic, we can prove things about, much easier, nice behavior for very long time integration. Again, Martin Berger is much smarter than me. We can, he looked at this and says, oh yeah, I can prove it easily. But again, I mean, these things have structure, and all I'm trying to say is, here, there is a structure. Not only that, the structure is, people have written about this kind of structure for many years. Can we take whatever people learn and explain these kind of things? Because again, remember, these kind of things are not really explainable. That's part of the problem, right? I mean, people don't really know how they're working, what they're doing. Can we look at all the other stuff and try to explain this? That's what I'm hoping mathematicians will do.
When you use this ODE or PDE ideas to construct the network, I think the learning assumption sigma should also have play some roles in the design of the
So sigma, of course, plays a role. I mean, people choose whatever they choose. There is usually two choices that people use, which is either LU or hyperbolic tang, more LU than anything else. Now, you can start to say, I want to parameterize this one, but it's actually, okay, so again, knowing after last week when I was talking to some real mathematician, it's really important that sigma will be monotonic. That seems to be mathematically very important, monotonically increasing. Now, if you choose any monotonically increasing function, apparently the properties will be pretty good most of the time. But again, I mean, what can you do more? I don't know. I mean, it's a good... Yeah, it will affect... Again, if it's monotonically increasing, then everything is be more or less okay, because there's, I mean, if you look at the derivatives, which is somewhere down there.
There's a diagonal sigma prime.
Yeah, exactly. So there is a diagonal sigma prime somewhere here. So this function, this derivative here is between 0 and 1, always positive, correct? Between 0 and 1. So it doesn't, so for example, if I take K2 is equal to minus K1 transpose, this does not really change anything, correct? Because it's always positive. So if you took a function that is not monotonically increasing, but monotonically and then decreasing, then for example, K2 equals K1 transpose doesn't necessarily mean much anymore. You get a lot of things that can happen. So monotonically increasing is very important. I mean, I only thought about it from a point of view of the Jacobians, but apparently for proving convergence of the PDE to something, you need it as well. So monotonically increasing is apparently important.
Last question? Michael?
When you go back to the original neural network picture with the dots and the lines.
You really like it? I thought we don't like it.
Go back.
Okay.
Recalling that. So a lot of times you see it, the number of dots changes. So
Yeah.
well, I know how to do that for matrices, but I don't know how to have an ODE with that.
So this is actually an excellent question, and let me try to answer it so there are two ways to look at it. One way to look at it is to say, so for example, in the ResNet, there are 3 blocks like this, right? So what they do is they would have like a block here, and a block here, and you say, okay, every block is an ODE that I connect between them. So I don't try to explain that connecting part. The other way to explain this is actually a bit more interesting. So if you ever looked at solving a heat equation for very long time integration, then in many cases, you start with some kind of a delta function. You have a very fine grid to represent that delta function. After you do a bunch of time steps, the whole thing becomes kind of very blurry, correct? Now there is no need to go to a particular very small mesh. So now you can basically make a coarser mesh. Basically, you're moving the size of the mesh, correct? And then you can continue on a coarser mesh, and people do it. So this idea of moving between resolutions is actually common in PDEs as well. So you can cast it in the same way. I never try to cast it in the same way. We just created, it's like, okay, I have 3 blocks here. But I think that there is work to be done to say, let's try to think about it as I'm basically working on a certain resolution. Now, look, I mean, I'm using a parabolic network. Things are blurring away anyway. I want to go bigger steps somehow. So like we do in multigrid, in ParaReal, for example, you'll say, I'm going now to use coarser mesh. And I will have to move to a coarser mesh. That makes sense.
Okay, let's thank Eldad again. And we'll move on to the reception. I think we should thank PIMS, Pacific Institute of Mathematical Sciences, INSERC, and the Faculty of Science at UBC that funds the Institute of Applied Math that's buying this all for us.
Who bought this? That's what we have to Who bought the food?
Yeah, that combination. Yeah.
in the middle. This guy is supposed to know.
When you go to different scale, like in the multi-scale approach, do you actually change the size of the convolution filters or just the input?
Just the input.
And I suppose, do you do any kind of max pooling? Is right at max pooling?
We do average pooling. It's basically, it's just basically averaging on the course. Like if you think about it,
But you don't stride it.